Hello everybody, this is David from SimScale. Thanks a lot for joining today's webinar. It's the third session of our air conditioning and ventilation workshop, and today we're going to talk about thermal comfort, the prediction of thermal comfort, and specifically how to do it with SimScale. For the ones that already participated in the sessions before, there might now come some repetitive tasks for you, but this whole workshop series got a lot of response, and a lot of people joined during the session, so bear with me. If I repeat a little bit of something today, I'll try to keep it crisp, but we start again with sorting out the technical things. So as a first step, we're using this GoToWebinar application for streaming this webinar, and you should now hear me, as well as you should see some slides which says Session 3, Air Conditioning and Ventilation. And if you can do so, if that works, could you quickly raise your hand with the GoToWebinar application? Excellent, I see a lot of hands, so that seems to work. So in case you can't hear me or you don't see the slides, etc., it's something on your end. If during the session the audio breaks down, etc., please use the raise your hand functionality. Also, one feature of this GoToWebinar is that you can ask questions at the end of the webinar. I try to cover them, but you can at any point in time during the session just type in your question whenever there's something that comes to your mind that you would like me to elaborate on. Just put it in there into the questions field, and in several breaks, as well as at the end of the webinar, I try to cover as much as possible of them, as many as possible of them. And we have a lot of users joining today, people interested in SimScale. So, and as the last sessions showed, it probably will not be possible to answer all of them, but I'll do my best to do so, to cover as many as possible of those. Okay. In the first step, let me quickly introduce myself. Again, for the ones that joined session 1, I also I presented session 1 as well. My name is David. I'm one of the co-founders of SimScale and serve as a manager and director here. I have an applied mathematics and mechanical engineering background, specifically in finite volume methods. So this is why I'm one of the presenters of this workshop, because I have my background mainly in CFD. And today, not so much about me, but rather about the topic of the session today. Today, we're talking about thermal comfort. So in the beginning, we're going to cover just very crisp, a little bit generic facts about SimScale as well as CFD with SimScale. I try to cover that very fast because for the ones that joined session 1, you will already know that. So I'll just briefly skim through those slides. And then starting at part 2, we're going to start covering a new topic today. We will talk about thermal comfort, so people involved in ventilation systems design or air conditioning design are always faced with the challenge of designing these HVAC systems, or designing and dimensioning these systems in a way that will make people in these buildings or in these in the rooms they design, in the office they design, with customers designing offices or building offices, they will always be faced with the challenge of making sure that people that are in these rooms, they feel comfortable. We're going to talk about a little bit more about how is thermal comfort defined, and then starting in step 3, we're going to actually look at one demo project, at a demo application that we will simulate together today. Also a hint at that point, we will do the simulation today together, so we will go step by step through. So I'm really a fan of live demos, so we will demo it live, but I would advise not to simulate in parallel or trying to follow exactly the steps I'm taking, because from time to time we will skip steps, specifically when it's about the computing time. The mesh generation will take a few, like 10 minutes or something. We won't wait that long. Also, the simulation run will take quite some time. We won't wait that long. So we'll skip these things, and we will make sure with a homework assignment that you can actually apply what you learned today, what you've seen today yourself, test it out, and get a feeling for how all of this works with SimScale. So that'll work. And then afterwards, I won't go through each and every analysis we prepared in a step-by-step live demo type of way, but I already did some post-processing, and we're going to walk through the results too also, because that's also a big part of simulation in practical engineering, right? It's the interpretation of results and what we can derive from it to make design decisions accordingly. And so this is then the result interpretation part. As a step 5, we're going to talk about the next homework assignment and where to find it. And as promised, the step 6 will be I'll try to cover as many questions of yours as possible. So much for this. They're already, let me quickly check on the first questions because we have the first questions coming in. Let me make sure. I get a bunch of hellos. Yeah, that's great. Hi there. So no urgent question. One urgent question maybe. We do record these sessions. Yes. So after this webinar, we immediately process the recording. We'll put it on YouTube, and everyone will get an email that will provide the link to this video as well as the link to the homework assignment in the forum. Last time, this took several days because we had a little bit of issues with the video processing, but this time we should be able to have that email with you within 24 hours, so that should work. All right, and let's get at it. Okay, let's very briefly here on these slides, because you might have seen them already. So this is SimScale, this is the team. We are located, I'm speaking to you from Munich, Germany. In fact, I think there's a webcam feature. Yeah, so hello everyone from Munich, Germany. I'm David. I'm speaking to you out of our little booth here at SimScale, where we record our videos, and we're located in Munich, Germany. So much for the webcam. So let's turn that off again. And what we are around 5 years old. We have meanwhile customers from over 190 countries. So the community is growing very fast. We have a very active community. But we'll talk about that later. 1 minute spent on why should we care about simulation. Very crisp, specifically looking at thermal comfort. Imagine you're responsible for designing the ventilation system or the air conditioning system for an office space, for a new office building, and you're facing the challenge of which cooling system to use in summer, which heating system. You have the constraint that it should be very energy efficient, etc. So you're faced with all of these constraints to your HVAC system, to your air conditioning system, to your heating design, but on the other hand, it's you that is also responsible for making sure that with every type of external environmental factors, people in this office space feel comfortable, right? So this is sort of the design challenge you're facing. So you're starting off with a design, and specifically when it comes to building prediction, building engineering HVAC system, it's very large-scale things, right? Oftentimes you don't even have the possibility to do physical prototyping. So eventually you just need to rely on, real-world experience or experience from past projects, similar projects. You can't even prototype it. So at some point after you ran through this design, you're making not so confident decisions that this might be the right HVAC system, and at some point you just need to build it. Yeah, this building will be built, the HVAC system will be installed, and this will be the moment of truth. If it actually serves the purpose, if people are feeling cold enough in summer, if it's warm enough in winter, and if there are complaints, etc. And often enough, there are failures in the field, right? Complaints. The HVAC system is not bringing the performance that was signed or that was agreed on with the customer, etc. So this is sort of the pitfalls of a traditional design process, and simply what simulation allows you is gaining more confidence during the design process by making sure that you get already performance data of your design, performance data of your HVAC system, how your HVAC system will will operate under different environmental factors, how, and you can do that immediately when you're sketching your first designs in AutoCAD or SolidWorks or Revit. You already, during the design phase, you can use your 3D models, you can use your CAD data and run a first simulation with it, see how it performs. You can predict all of these sort of different, during summer, during winter, with different window layouts, etc., how residents, how people in the office space you're designing, how they will feel. That's sort of the edge simulation gives you, to put it that way, right? And ultimately, this is money in your bank, because you can run more cycles of this. You can make sure that your design is actually fit for purpose. You can run more of them. You can do them earlier. You risk less failure in the field, less complaints, and ideally, you by testing more scenarios, by testing more design variants, you can ultimately ship a better product, right? And this is sort of ultimately gives you a competitive edge and is money in your pocket. And this is what it all comes down to. So in the bottom line of simulation, it allows you to design better, faster, and cheaper. That's sort of the mantra of simulation, right? And here in this case, this is our prime example of a valve. Might not be the best example for that specific scenario when we're talking about thermal comfort, but the bottom line of it, designing better products faster with less money spent, is always the same. So this is why this slide, I guess, is a good summary. Very crisp for the ones that joined the last sessions. There's a ton of simulation tools out there, a ton of different simulation software vendors. So why is there another one? Why now SimScale? And ultimately, what we are doing differently is that we are trying to make simulation accessible to everyone, right? We do think that the traditional process, the traditional way how engineering simulation is been delivered to the customer, its buying experience, its usage experience, is fundamentally flawed, and leads to the fact that simulation has not yet become a standard tool for so many engineers, for so many architects, for so many designers out there. And we're trying to change that by first making it more accessible. So with SimScale, you don't need any software, any specific hardware locally. The only thing you need is a web browser. Cost efficient, the pricing model of SimScale comes with a very low initial financial commitment. In fact, there's a free community tier that allows you to simulate completely for free. In that case, your simulation project is going to be public, but it's great for testing, it's great for community usage, great for hobby projects. And then once the paid tier allows you to keep your simulation work confidential, so to have private projects, and that starts at 2,000 euros annually, and then you can buy more computing quota. So basically the cost for SimScale only scales with the value you get out of it. So it's sort of a much more flexible and more scalable pricing model that allows more people to participate, that makes it economically feasible for more projects, for more companies. That's what we mean with cost efficient. For everyone, on SimScale, and we're going to see that later, is due to the fact that we have this community model, this community plan that allows everybody to start for free. SimScale is essentially a database of thousands of simulation projects. We just passed 20,000 public simulation projects, and they are accessible by you just via a web browser. So you can go in there, search for similar projects, interact with your peers, interact with other engineers, designers that face similar challenges, and all of them on the same place with the same tool. So this is what we mean with for everyone, right? So this not just another software, but essentially a community of people working with the same tool, working in the same place, being very, very close to each other, by everyone working cloud-based. That's sort of what we mean with for everyone. Okay, and then we're going to talk specifically about CFD today, but in fact SimScale is a general purpose simulation environment, so it ships structural mechanics analysis types, flow simulation, thermodynamics, acoustics, and particles. So we're covering these 5 disciplines, but CFD is sort of one of the main or used by many customers of ours, and specifically looking at CFD, we cover a wide range of fluid flow phenomena, as well as advanced applications for different sorts of engineering applications, for different sorts of industry verticals, and we're going to see them later today in action, and here are some some pictures. So just like to pick some of them. This is a, I think there is this neat show tool. Let me quickly see, highlighter. So this is a passive scalar approach. So we do see a mass flow, so a particle, a mass flow being distributed in this flow. This is a compressible flow around an aircraft at cruise speed, right? Here we are having a particle phase within a flow field. This is a rotating machinery, so we're having a pump where the impeller is actually rotating, and by that driving fluid through this. This is an external aerodynamics application, so incompressible. We've got multi-phase flow, so this is a solid body movement. So that tank actually moves around, and you can see the tank sloshing happening. In fact, this is something close to our homework. So this is the cooling side of a refrigerator, and this will be part of the homework. What else is there? Here we've got again a marine application. We've got thermal, right? We've got moving meshes. So all sorts of different phenomena are available within CFD. So that's being that. How can I remove now this? Erase all drawings. All right, but back to the topic. Thermal comfort prediction. Why thermal comfort? And when you join this this webinar, the chances are high that you're actually involved into some sort of design process where you do care about ventilation, heating, cooling, sorts of phenomena, and one of them is one design or one performance characteristic is thermal comfort within a room, within a space where people are, right? And the motivation for this is sort of that in modern office areas, in modern buildings, you want to provide a great experience for people walking there, working there, being there, specifically when it comes to offices, where you just can increase the health of these people, where you can make sure that work efficiency is high. So for modern office spaces, for modern spaces, you just care about that. And there's an official definition of the thermal comfort factor, and there are essentially 6 different criteria coming together when you're saying when a human being in a room says this is this is comfortable or this is not comfortable. And there are 4 environmental factors, so that depend on the room. So this is what you can basically influence as an engineer. And then there are 2 personal factors where it will be hard for you to influence that. Let's quickly go through them. So the first 2, I made them bold because we're going to look today at them, is air temperature and air velocity. So basically whatever heat is being transported, say in summer the heat is being transported from the room away, so that you cool the room temperature down, or in winter from your radiator or from your heating system to the human being, is essentially the convective the convective heat transport. And so that the temperature the air has once it touches your skin is the air temperature this human being will feel. Same with the air velocity. Independent of the temperature, the faster the air passes your skin by, the sort of the felt temperature goes lower, right? We all know that from standing in the wind. And then the other 2 factors that we will not look at today is radiant temperature. So there's not just heat being transported to your skin via convection, so via air particles moving from the radiator to your skin, but also via radiation, so directly via waves. And the 4th environmental factor is the relative humidity. So how humid the air around you is also impacts the level of comfort the human beings feel inside the room. That's sort of the 4 things you as an engineer, you as somebody responsible for designing, for dimensioning these HVAC systems, can influence, can predict, and by that make sure that people within the room you're designing feel comfortable. The 2 other factors are personal, right? I mean, you will have a hard time saying how people will clothe or how people will dress up within the room you are, as well as their personal or individual metabolic heat. This is really personal factors that you don't have under control as an engineer. So how can now CFD help in all of this? And with CFD, with flow simulation, essentially what you can do is whenever you decided on a specific technology that you're going to use for cooling down a room or heating it up or ensuring you know, a certain air age inside of the room or whatever you're asked to design there when it comes to the HVAC system, CFD allows you to predict, to virtually assess whether or not your HVAC system actually delivers the thermal comfort that you want the human beings to feel inside of this room, right? You can, for example, we had customers being involved in testing a very innovative kind of cooling system for rooms where they did, you know, where you can test, okay, what about underfloor cooling, heating? What about cooling panels at the top of the room? What about, can I maybe use a passive cooling system as opposed to an active cooling system, which would be more energy efficient, etc. So all of these what-if scenarios, you can test these what-if scenarios during the design phase. You can make your design changes, run a quick analysis and see, okay, how will this impact thermal comfort of human beings within this room? This is essentially what allows CFD, what brings, or why it makes sense to incorporate CFD in your design process. Obviously, you will see 3D weather maps of the velocity field, of the temperature of the air, and so by that you can sort of trace back to, are there specific hotspots or cold regions or even air currents within the region of interest, and you can predict all of this just based on your CAD data, right? Coming out of AutoCAD or coming out of Revit. That's essentially what it comes down to. Okay, now. Enough theory, enough motivation, let's get our hands dirty. This is essentially the case that we're going to look at today. This is a simple living room, or call it whatever you like. It's essentially a demo CAD model, a demo model that we're going to use to predict thermal comfort in this room. And what we can see is that we have the settings, that we have a very small room. And there's the radiator on the one hand side, and then there's here's a couch on that side, and probably this is the region of high interest because people will spend their time here, right? Essentially, and you can see again, it's a very small room. It's a minimal example because the way how we're going to mesh this today, the way how we're going to set up the analysis today, can be essentially ported to a lot of different models. Whether you're dealing with HVAC system design for vehicles, for you know, trains, cars, or trucks, or let it be office spaces or specific buildings, say halls or entrances for very special buildings, etc. The analysis, the way how you do that is always the same. What we wanted to make sure using this example is that there is a certain level of detail, so you can see that this radiator is quite detailed here. But not too much detail to speed up or to not slow us down when meshing, to not slow us down when run the simulation. Okay, and what we're going to do today is we're going to look at 4 different scenarios, and again, what-if scenarios, right? The first one is we're going to look at this at the minimum, sort of the baseline case, the standard setup, and for this, we're going to heat up the radiator to 40 degrees Celsius. We're going to have all other walls cooled down at 60 degrees Celsius. So you can imagine this as a very, let's say, badly insulated room because the walls get very, very cold, right? We assume simply at steady state, we assume that the walls are very cold and the radiator is that, and we're interested in what type of velocity field is being generated in this room and what kind of temperature distribution is this heater able to provide within the room with badly insulated rooms. That could be sort of the scenario, right? And in the second step, what we're going to look at is we're going to compare this with a window installation over here, and the window naturally being a worse insulator or insulator against the cold outside, so it's sort of a winter scenario, so it's colder than the rest of the walls, and we are interested in what kind of impact will this have on thermal comfort inside of the room. In a second scenario, we're going to look at the impact of a different type of insulation. So we're going to have in each scenario, we're going to have the cold window, again at 5 degrees, but this time we have one scenario where the walls are not well insulated, and then one scenario where we do have the walls insulated better. So walls and furniture are up at 20 degrees to see, okay, what type of impact will the radiator have? What type of average temperature will I be able to produce with this amount of heat being introduced in here, right? And we can see now that we did not talk about different types of heat fluxes across these walls. We will not talk about different types of, where we bring in hot air or suck out cold air, or we will not have any inlets, any outlets. We don't talk about transients analysis, that sort of stuff. We really keep it very, very basic to understand the analysis type, to understand the workflow. All of this is shall serve as a first analysis, and we will provide you with the full analysis setup as a public project, and also the homework will have a step-by-step process, a step-by-step tutorial that will walk you through. The idea here is really to show you one simple example, but full example of how to predict thermal comfort within a room. That's the idea. Okay, how will we test these, or how will we do this on SimScale? And this might also be, ideally, some things are already familiar with you, for you when you've already used SimScale, but the essential workflow is always very, very similar. We start by bringing in the CAD model. You can either upload it, or there's a direct connection with a cloud-based CAD model called Onshape. You can bring it from there as well, but you start with your CAD model, and then the next step is CFD on SimScale is done, or most of the analysis types on SimScale when it comes to flow simulation do use a numerical method which is called finite volume, which is called the finite volume method. And people are very familiar with the finite element method for structural mechanics. And the finite volume method is sort of a very similar method that is being the dominant method to be used in flow simulations. And so for using such a finite volume method to predict, to simulate actually the moving air in this room, we're going to need to discretize, so to divide the area of interest in many, many different small finite volume cells, right? So all of this is cells, and this step is called meshing. We're going to look at this later together. And so we generate a mesh, a computational mesh that will allow us to run this simulation. You can see that around the radiator we applied quite some detail in the mesh. The rest is rather coarse. And then we're going to set up the physics, which will be rather simple today. We will have a hot radiator here, and we will have the rest of the walls being at the same temperature. And as a last step, we will then be able to interrogate the results that were generated. So we can see here the velocity field, how air rises here, and then sort of generating this big swirl here. That's sort of the interpretation of the results, which is the third step. Okay, and we're going to walk through this together, and the homework that will be sent to you will allow you to walk through this process yourself on your own, to really make sure that you've understood, that you've grasped what was talked about today. As I already mentioned, you can either bring in the CAD model that you want to simulate from your local desktop CAD software, so SolidWorks, AutoCAD, Inventor, all. We do support natural or standard exchange formats for CAD data, so you can just import them. Or this here shows our natural integration with Onshape, which is a completely cloud-based CAD software or CAD system. So you go to onshape.com and you can model there as well. And as you can see, this then allows you to bring in your CAD model directly from Onshape and then simulate it in SimScale without the CAD model ever touching your hard drive. So that's sort of the great example or great advantage of using everything completely cloud-based. To already know what sort of like a short summary, what's going to happen in the next 15 minutes is, first what we're going to do is we're going to bring in the CAD model and generate a mesh for it. So a computational mesh, we're going to divide the region of interest, our CAD model, into many, many small finite volume cells. And this is called meshing. We're going to use a hex dominant parametric approach. We're going to hear later about what this is in more detail. Once the mesh is being generated, we're going to set up a simulation using a low compressible buoyant flow solver. So this means low compressible means we do not expect any, velocities in this flow field that will even come close to the speed of sound. Once you're coming closer to the speed of sound, say 0.3 Mach or even 0.4, then you cannot consider this flow anymore low compressible. Then it's a real compressible flow, and you will have all sorts of interaction at Mach 1. You will have shocks in your flow field, but all of this can be neglected when you're below 0.3 Mach. And I mean, we all know that from our own living room. We don't have any hypersonic shocks in there, so the velocities are rather low, the Reynolds numbers are rather low, so we can use a low compressible solver, but that respects buoyancy, because buoyancy, hot air will rise, cold air will go down, so this is important. So it's a buoyant flow solver. So density is being basically varies with temperature, but it's stiff coupling with pressure. This is sort of the mathematical words behind it. What we also, that's an important concept to understand as well, we will not look at the transient simulation. And let me quickly bring up, because actually in the SimScale forum, because we did run this simulation transiently, just to make you better, to give you a visualization what I mean with transient, I'll quickly hop over to the SimScale forum, and I actually posted an animation of the transient process here. So this is the model we're looking at right now, right? And you can see that this is a transient process of this. So it really starts from a specific time point. So at 0 seconds, the room is completely standing still. The temperature is at 20 degrees Celsius, and then the radiator starts heating this up, right? And you can see that over the course of 10 minutes, this radiator is being able to quickly bring up the temperature of this room, and we can see how long it takes to bring up the temperature of this room. This would be a transient modeling of this, right? And you can do that yourself. SimScale is capable of doing that. There is a public project where you can look into how this is done. But we will focus on today is really a steady state flow. So we are just interested in the final state of the system, so the equilibrium state of the system, or with other words, what happens after an infinite amount of time, and how does this system look like? How is the temperature distribution? How is the velocity distribution? And in real world engineering projects, this is the typical way to go, because steady state simulations where you just are looking at the last, at the ultimate equilibrium state and not at the exact way how the system arrived there, due to this fact, it's much faster. It's computationally much more efficient, and this allows you to run much more simulations faster, and specifically in early design phases. So during the conceptual design, it does not make, or it oftentimes makes no sense to run this very, very detailed transient analysis, because the only thing you want to identify is, are you sort of on the right track, right? And then you want to run many iterations of it. And here, the steady state analysis gives you the much better tool in these early design phases. Once you're close to being, design needs to be delivered, you're coming closer to the deadline, then what you might want to do is a last transient analysis, a dynamic analysis, like the one I just showed, like this one, to make sure that also the ramp-up phase is correct, etc. That's sort of the difference between transient and steady state. We do expect turbulence to occur, so we're going to use a k-omega model and to predict turbulence. What we're going to see afterwards is what we will neglect is radiation in this field, right? And we will also not look at humidity. So the thermal comfort that we can predict, or the parts of the thermal comfort that we will be able to predict, is what type of velocities will we have in different parts of the room. So are there any high air currents, where we have a ton of velocity going on, a ton of movement going on, and how is the temperature distributed, etc. So this is what we then afterwards gonna see. All right, so much for the, let's say, dry run, and now let's actually start setting up the simulation together. And for that, let's really start from scratch. I'm gonna hop over to simscale.com. And for the ones of you that already have a SimScale account, you already know that. For the ones that have not yet signed up to SimScale, the only thing to follow the steps I will show, or to test this out yourself, is simply really open up your browser and click in the top right on Create Free Account, and this will allow you need to fill in a little bit of information about you, and this is all you need to do to log into SimScale. Or to start simulating with SimScale. It's really, there's no software, there's no hardware, it's just your web browser. If you have already an account, what you want to do is you click on Login. I already logged in a minute ago, so I'm automatically brought into SimScale. And this is how SimScale looks like. Quick overview. There are 5 main tabs here at the top. Where you always start is your dashboard. It gives you an overview over the latest projects you've been working on. You can see I prepared a little bit of something for this webinar today. It gives you an overview of what's going on at the forum right now about your computing quota, and as well as your latest simulations that you ran. Switching over to the public projects, this shows you the 20,000 public projects I talked about. All SimScale uses a lot of engineering people in your engineering professionals running simulations on here, so you can use them, you can check each of them out. You can, once you click on it, you can see a 3D model of it, you can rotate it immediately, right? You can see if this is valuable to you. Oftentimes there's some comments from the users, so you can scroll down here what these people did, etc. So this is sort of the public projects that you can use as a sort of as a database for your own projects. So you can just copy one that is very similar to what you want to do and reuse its simulation setup. That's the idea behind these public projects. There's the forum, where tens of thousands of users are interacting on a daily level with each other. We have some help, documentation in your profile. Okay, so much as an overview, and what we'll do today is we're gonna simulate this living room. And for this, I'm opening a project where I already prepared a little bit of something in to make sure that we don't waste time, this precious time in this webinar, waiting for the mesh or the simulation to finish. And what I will do now, roughly for the next 15 minutes, is I'll walk you through the 2 important sort of setups that you need to do for such an analysis. The first one is generating the mesh. The second one is setting up the physics. Okay, as you can see, we already brought in our living room, so we can see we have this, we have the couch over there, we have the radiator here, and that's sort of how this looks like, right? It has different solids, and I imported it from Onshape. We won't do that today, and what I already did is I created already some selection sets, some topological entity sets. So I selected the radiator faces, these guys down here, right? All of these guys are, come on, all of these guys. I selected the slabs, so these guys, and over there, let me quickly switch back to another visualization. Okay, so I selected the radiator sets, grouped them together. I selected the slabs here, grouped them together, and all of the rest of the faces. Why I did that, you will see it in a second, because I'm going to apply different levels of refinements to those. And this is the reason that I already grouped them. So and now let's generate a mesh for that. As I said, the first step to running a finite volume simulation is actually generating the finite volume mesh. On SimScale, everything that works with a right click always works via a left click. So this is the geometry here on the left. Maybe one thing before we move on. The SimScale interface for simulation is divided in 3 main tabs. There's the mesh creator, in which we are currently, where it's all about CAD import and mesh generation. there's the simulation designer, where everything is about setting up the physics of your simulation. And then there's the post-processor that allows you to analyze the results you simulated. Okay, so, and what we're going to do first is we're going to generate now a mesh for this. So I'm going to click on my CAD model, and I click on New Mesh, and this will automatically create a new mesh here on the left, which it automatically called Living Room Mesh. Let's call this Demo. That we keep some bookkeeping here. And what you can see in here is that there's mesh operations under it, and then there's operation 1. And the operation essentially defines on how this mesh will be generated, what algorithms, what algorithm will be used, what types of refinements you want to see, etc. That's sort of what the operation defines. And what we use today is we will use the hex dominant parametric approach for generating a mesh. And now I'll save it immediately, and now we're going to go step by step through this to set this mesh up. And in the first step, what we're going to do is this model, this mesh operation, essentially works with how this mesh operation generally works is it starts with a background mesh. So it starts with a normal Cartesian mesh being generated in the background, and then it starts snapping through to the different faces in here. And then there are some other faces, but the fundamental concept is that you start with a background mesh, so with a Cartesian grid in the background, and then this Cartesian grid in the background is being refined as you like it to be refined. That's sort of the general approach. Yeah? This is why I wanted to show you this base mesh box. This looks good. And so what we're going to do is, the only thing we need to do is we're going to now apply different levels of refinement to this, to different parts of the model. So I'm going to go directly to mesh refinements. And I say, I want to create a new mesh refinement. And there are different types of mesh refinement. Oh, did I click? There are different types of mesh refinements available, and you can see that I can give each, no, a bit slow. There are different types of mesh refinements available. So the first one, I'm going to call this is my radiator refinement. Yeah? I'm going to call it radiator refinement, and I will apply a surface refinement, which means at this specific surface that I'm assigning to this refinement, I want to get more fine cells or finer cells than in the rest of the area. So in that case, I want to have a level of refinement of 4, say 4, and I'm going to hop over to face sets, and I'm going to say radiator. And when I click the select assignment button over here, the great thing about this is that I can see now, these radiator faces, the ones that are red, will now be refined to a level of 4. Without going too much into detail, the higher the level, the smaller the cells at the specific face, right? So that's sort of the logic. And since here I'm having, I'm expecting a high temperature, right? So high velocity differences close to this radiator. There will be a boundary layer, a turbulent boundary layer that's going to happen here. So I want to have very fine cells here. So this is why I'm going up to a level of 4. I'm going to save it, and we're set with our first refinement, right? Now the second refinement, I'm going to say, okay, these are my slab refinements. Let's call them slab refinements. Again, I'm going to choose a surface refinement. I'm going to only refine my slabs to a level of 2. Again, choosing these guys, and we're set. Slab refinement done. Next refinement up. And this will be our, this will be the rest basically. So surface is rest. I again choose a surface refinement, and I only refine it to a level of 1. And in that case, I called it level 1. Okay, so this now essentially means that the Cartesian grid that is being generated in the background will be refined to a level of 4 at the radiators, to a level of 2 at the slabs, and to a level of 1 close to all other walls. That's essentially the logic. So with these refinements, you can steer the number of cells you want to have in any of your areas, in the areas of interest, to a very to the very detail, right? Specifically, when you have more complex models, you might tune these refinements, you might apply more refinements to specific regions of interest, so this gives you a lot of flexibility when generating your mesh. As a last step, and then we're set with mesh generation, we're going to generate layers. And these layers essentially means, show all, these layers means that what we want to have is close to all walls, we will expect a turbulent boundary layer, right? Or at least some sort of boundary layer, because close to the wall, we're going to see no movement because the air molecules will stick to the wall. But a little bit away from the wall, we're going to see all sorts of convective heat transport, convective velocity effects. And so between this velocity close to the wall and the zero velocity directly at the wall, we will have a velocity gradient, a higher velocity gradient. And to capture this gradient better, to capture this near wall action of the flow field, we want to have more cells close to all physical walls. And we do that by bringing in a layer addition type of mesh refinement. And for this, what I'm going to do is I'm going to select simply all faces and assign them. That's all there is to do. And we're set. So this was now 4 different types of refinements, and I'm set, and I can now start this type of simulation. Yeah? Sorry, not this type of simulation, this type of meshing. This was all there is to generate from CAD model to generate a HAX dominant mesh, or such a polyhedral mesh for a finite volume analysis of the flow field. And you can see in the lower left, the simulations, the meshing is started, it's being computed, and I get real-time notification on the progress. I'm being updated, and once it's over, this will take maybe 10, maybe 12 minutes, and then we're set. But we don't want to wait that long, so what I'm going to do is I'm going to hop over to a project where I already have a completed mesh, and this is, I think, this one. All right. First step done, we generated a mesh. This will come back, and now I'm going to show you how this looks. And this is this guy here. So here you can see in this mesh setup again, I have the base mesh box exactly like we just defined, right? I have the surfaces, the level 1 refinement, I have the radiator refinement, I have the slab refinement, I have the layer refinement. So exactly what I just did. And here you can see now that we have a finite volume mesh being generated. So we can look into it, we could now slice it, etc. But we're running a bit out of time, so I need to speed up a bit. And here you can see all these, the refinements that I applied. So you can see that close to the radiator, I have the detail of the radiator with the level 4 refinement assigned. I can see that the slabs, can you see that the slabs got a level 2 refinement, so all of this worked nicely. So this is exactly what I wanted to have. Okay, and now what we're going to do is we're going to set up a simulation together. And since we're running a bit short in time, I just will concentrate on the important steps of the simulation setup, that we can spend the last 5 minutes of the workshop to really engage in post-processing. Okay, I'm going to spend now 5 minutes on the simulation setup. So what we do is we hop over to the simulation designer and we start a new simulation. Living room, no window. Demo. Simulation is being created on the left, and you can see again a very clean user interface, right? We do not want to burden or put the burden on the user that there's a ton of icons here at the top where you need to know what it is, etc. It's a template-based workflow, and the first thing you need to do is you need to choose your analysis type. So what I do is I flip to fluid dynamics, I choose the natural convective heat transfer analysis type. There are some detailed settings to be done. So the first thing is I'm going to choose a K omega SST turbulence model, and as discussed, we're going to choose a steady state analysis. And now I would like to draw your attention over here to the left to this tree when I hit save. I click save, and you can see that the tree of this analysis type, that essentially now a template is loaded that provides me with all the settings, all the options that I now need to decide, but not with more. This is this template-based approach of SimScale. So I can really start from a template, and I don't have to start from scratch. Yeah? And so the logic is always the same. Green means it's already done. Red means you need to do something. Blue means you can do something. Okay, let's go through that. Domain means which mesh do we want to use actually for our simulation. We want to use the first one that we generated. I select it, hit save. It's automatically being loaded over here, right? One thing I did already as a preparation is I already created some topological entity sets. And essentially what I did is hide selection. I grouped them in two sets. The first one is the radiator over here. So that's that guy, right? That's my heater selection set. And all the rest of the walls, these guys are the rest of the walls, right? Very, very simple setup. We want to keep it basic today that you understand the fundamentals. Okay. That's sort of, we chose our mesh, we're set here, everything looks blue and green, that looks good. Moving on, model, it's important, let's not forget about the gravity. Gravity is in negative y direction, right? Negative y, so minus 0.81. We'll save, and we're set here. Next one is materials. We're adding a material by clicking on new over here. And you can see that since we are running a thermal analysis and not an isothermal incompressible analysis, we do see there's quite some things to be said. But good thing is that we can simply import. We have some basic fluids provided in the material library, so we can import that. It's being automatically applied, right? And the only thing we need to do is we need to assign it to our model here actually, right? In that case, since we only have one region, it's pretty straightforward, right? I apply this material to this region, and I can also check on it, so I can select it and see, yeah, that's the right region. In that case, since we only have one region, that's trivial, right? But sometimes when you have a conjugated heat transfer analysis or you're doing structural mechanics with a larger assembly, you have a lot of parts here. Okay, next up are the initial conditions. And we will leave all of them the same thing, right? Keep in mind, we're running a steady state analysis. Steady state means we're only interested in the final equilibrium state of the system. So the actual initial conditions only help us to sort of speed up our simulations. But there are scenarios where they are more important. But in a normal setup, in a normal settings for a steady state simulations, the initial conditions only help you to speed up your simulations, but they don't impact the final result. So in that case, we leave, we might check on temperature. No, but everything is fine. We leave everything as it is. And we're going to directly jump over to boundary conditions. What I do is, and again, keep in mind, everything that works via right click works also via left click. So I can use this button, I can use a right click, the context menu, doesn't matter. Okay. And so that's the last step I want to show today, how to apply such a setup. Keep in mind, that's the basic, very, very simple setup where we say we're going to have the heater at 40 degrees Celsius. We're going to have the rest of the room at a badly isolated 16 degrees Celsius. And so how are we going to do it? So first I want to take care about the heater. I call this boundary condition the heater. And you can see that there are different types available. In our case, and we're going to use the most advanced type of boundary condition, which is custom. And custom, and you can see it, I'm calling it the most advanced because velocity inlet would be rather straightforward, right? I would define a velocity, I would define a temperature, and then I would be set. But we're going to use something very specific, and so this is the most powerful, most advanced boundary condition because it allows you for every type of physical quantity that is relevant in the problem at hand to define what exactly is happening at this boundary. And in that case, at the heater, what we're going to do is we're going to fix the velocity, obviously at 0. And you can see each of these physical quantities has a ton of different options. And in our case, and this is why ideally you don't need the custom boundary condition. But in our case, since we're having a specific one, we're going to need it. But most of the time, the other ones are easier. Okay, velocity, we're going to apply a fixed value. which means we'll, directly at the heater, we want the velocity to be 0, right? Essentially, it's a no-slip boundary condition. That's everything there is. Pressure, we're going to apply a fixed flux pressure, which is the most advantageous for this type of walls, for the no-slip walls in these buoyant flow simulations. And this one is the actual engineering work here. What about the temperature? We're going to apply a fixed value temperature at the heater at, what did I say, at 330 degrees, which is exactly 40 degrees Celsius, right? We're talking Kelvin here. All the rest goes to wall function. We're going to set all of this to wall function, wall function, wall function, nothing more to be talked about. The good thing about these wall function is that they don't have any parameters, and it essentially comes down to turbulent modeling that we don't cover today, but these wall function are sort of the standard boundary conditions that you use at the wall whenever you're dealing with a turbulent boundary condition. There's a little bit of more theory to this, but we won't cover that today. Okay, and the last there is to do is clicking on the heater and save. And we're set. So essentially what we just did is we set our heater, the air will stick to the heater with 0 degrees Celsius. We're going to have a fixed temperature of 40 degrees Celsius, with 0 meters per second velocity. And we're going to have a 40 degrees Celsius directly at the heater. That's sort of what we just did. And the same thing we're going to do now for the rest of the walls. So cold walls, badly insulated, again, custom, and we're going to switch the fixed value. We're going to keep all of them 0. We're going to apply the fixed flux pressure for pressure. We're going to apply the fixed value of, what did I note down? 290 degrees, that's 20 degrees Celsius, and the rest goes to wall function. Wall function, function, wall function. And we're going to say, this is our walls. And we're, there's some details that would now to be done, but the engineering work essentially was just done. This was the important point, how we set up the boundary conditions, right? And then again, in that case, we have only fixed temperatures. You could now go into, different terms of heat fluxes, different adiabatic walls where the temperature is being developed, non-adiabatic walls, etc. So there would be all sorts of scenarios you can model through that. And this is the actual engineering work. This is why I wanted to make sure that I have it covered. Okay, essentially what we would now do is we would start a simulation run down here, and it would essentially work the exact same way as we just started the meshing process. So we would start it, it would run in the cloud, and once it's over, it would come back with the solution fields. And for that, let me quickly hop over to another project, and I'm running a bit short in time here, but bear with me we might need 3 more minutes. I'm sorry for that it takes a bit longer, but I just want to make sure that we've seen once the complete workflow. So we've seen the mesh generation, we've seen how the simulation was set up with this very simple scenario, but more complex scenarios will work essentially with the same workflow. You would use other boundary conditions, you might use other initial conditions, but the work is essentially the same. Okay, and once this comes back, you then can tap into the post-processing results, or into the post-processing tab, which allows you to analyze, visualize, interrogate the results of your simulation. And so I also want to make sure that you have a feeling for this as well, that you've once seen the entire workflow of SimScale. So this is now, and you might notice that the interaction with this scene, with this sort of result works a little bit different, because this is now server-side rendering. We're having millions of cells, and all of the heavy lifting is done in the cloud, is done on a remote server that is very, very capable, that is a very, very large server, right? And here you can see it that I now have, and again, I'm in my Chrome web browser, right? And here we can see now that this is the temperature, this is a slice visualization through the radiator. I have the hot radiator down here, and we can immediately see the temperatures being transported to the top, right? Sorry, is that actually temperature? Let me quickly flip over. I'm sorry, this is now, this is velocity. So you can see that, let me quickly check, where is the scale? this. There you go. So this is the velocity. So we can see that that around the radiator, the air is moving up and is sort of forming this large swirl in this room, right? So this is what we can see here. We can flip now through different different sorts of results visualization, and can check on the temperature as well. So we can rescale. Let me quickly rescale a bit. Say 200 and let's say 200 Kelvin. 295 Kelvin. Here we can see that the radiator we are very hot, right? You can see it here at the radiator we're very hot, and now going up, the hot air is convectively transported to the top, moved around, and we can see that rather at the top the air is the room is hot, and rather at the bottom the air is cold, which we would normally expect, right? This is sort of like the end-to-end workflow through SimScale. These results, and this is the type of simulations where you use, this is what we expected, right? It's not that there are big surprises of what we just see. It's just, it serves as a demonstration purpose that actually with simulation, with SimScale, you can, just by using your web browser, you can predict air velocity and air temperature, which are both fundamental to predicting thermal comfort inside of your HVAC system, right, or what your HVAC system leads to. So that wraps up the live demo part, and just the last 60 seconds to 2 minutes, I want to quickly go through this, right? This is a little bit of post-processing now done before I answer questions. This is the transient heating of this, right? We can see here after 20 seconds, after 5 minutes, after 10 minutes. And we can see that initially the air is being heated up, and we're seeing that hot air is transported to the top. As we would expect, hot air stays at the top of the room. It cools down a bit over here, so it goes down, and this swirl starts happening, or this vortex is being generated. And this would allow you to see how long will it need to heat up your room to a comfortable level, would be an answer of such a transient analysis. Moving further, this was, can you remember, this was the case one that we wanted to analyze. So we have the heater at 40 degrees, we have the walls at a lower degrees Celsius. This is exactly what we just analyzed, right? And this is the steady state. So after, in a steady state system, we have an average room temperature of 16.9 degrees in that setting with badly insulated walls. And we can see that the vortex is not really there. So we can see this, the velocities, we can predict different velocities in different areas of the room. And with the cold window here, obviously we'll get a lower average room temperature. We see a little bit of a changed velocity profile here. Now we could look into different scenarios. What kind of radiators do we want? What kind of insulation do we need, etc. That's sort of the case one that we looked at. Again, this is not like shocking results. It rather shows you how you can now go through different what-if scenarios with SimScale. Looking at case 2, a different type of insulation. Again, we have the window at outside, it's winter, we have a very cold window, we have the radiator here, we have the flow happening, and a bad insulation, so the walls are very cold, and then we have a better insulation on the right. Average temperature obviously immediately rises, and interestingly enough, we have a bigger swirl or a bigger vortex happening, so we would now need to check in, okay, is it are there significant velocities that are being generated, etc. This is something now you could tap into. Okay, so much for the sort of result interpretation thing. As I said, very, very basic examples, but the good thing with SimScale, again, is the setup of a more complex or the simulation of a more advanced type of model with the workflow is very, very similar. Obviously, there might be different boundary conditions. You might need more time for meshing. You might need more surface refinements, etc. But the fundamental workflow is very similar. All right. And then we're concluding 5 minutes too late the official part of this workflow and of this webinar. And this is the introduction to the homework. And this is obviously an optional homework. Nobody's forced to do it, but we do think that simulation is best learned, or SimScale is best learned by really doing it yourself. And the great thing is that SimScale completely comes web-based, so no installation, etc. You can just have it on your laptop, on your couch at home, ideally in a thermal comfort area, in a comfortable area, and there you can just, you know, follow the homework, and it's a very detailed step-by-step analysis of a similar case. So it's about a kitchen where we have a refrigerator here, where we have the heat being transported away from the refrigerator here, where we do have, again, a cold window and also a stove over here. And so then it's about what type of velocities are being generated, what type of heat is being generated, etc. So thermal comfort inside of a kitchen. That's another basically another use case of this. And the homework will walk you through, and you can then also submit your homework to us. An engineer on our end will check on it and will hint you to possible modeling mistakes, the things you could improve. All right, that concludes the official part of the workshop. I'm sorry again for the 5 minutes too long, but I hope this gave you a feeling, an understanding, a fundamental understanding of how SimScale can help to predict thermal comfort, how the rough workflow looks like, and it gave you sort of a head start in now using SimScale yourself and testing it yourself. That's sort of the idea of this workshop. All right, and for the time being, I would quickly go through some questions. And again, I'm seeing that there are many questions, so we won't be able to cover them all, but I'll try to at least cover some of them that we can go in here. Okay, so somebody says that he or she or one participant says that he missed the first sessions of this. Let me quickly show you how you can get there. So on simscale.com, on our website, there is a tab Learning here at the top right. And if you go on workshops, one of the currently running workshops is that one, right? CFD for HVAC. And if you go here to register now, you can see this is sort of the hub page for this webinar. And down here, you can see all recordings of the past sessions. You can see all tutorials for the homeworks. You can see where to submit these homeworks for an applications engineer on our end to check on them. So here, everything is summarized essentially. That if you, and there's no, we have all of these recordings, right? You can tap in. You don't need any like credentials or something. They're hosted on YouTube, so you can just click on it and watch it. So that's the first session, etc. Yeah, so that should be the first thing. And the other one you should know is I really recommend joining the forum. So on the forum, there's a ton of different analysis, and one of them, one hint immediately is this guy, right? This is exactly the homework assignment that we just talked about. So this is my colleague Sam put together this homework. So it walks you step by step through this setup of this kitchen analysis. So this is the second thing, and within the forum you can find also the other one. So there's session 2 homework somewhere down here, etc. So everything is recorded. You can tap into everything, so that should be fine. Somebody asks regarding the schedule of this workshop. Let me quickly again go back to this heating. What was it? Ventilation? No. The overall schedule. So this workshop has 4 different sessions. This was the 3rd one. So the first one is even like past. That was about a cooling of a data center. Now the session 2 was 2 weeks ago was on smoke propagation. Session 3 now was on thermal comfort, and next week's so July 26th, this will be the last session, is contamination control of a clean room, where we will look into how a passive scalar is being transported. So this was session 3 of this workshop, but we record everything. So even if you now joined the session 3 and you missed the ones before, not a problem. We record and we collect all resources that you need to go through the other sessions as well. So that All of this is collected here, and it will also be included in the email that's going to be sent to you within the next 24 hours. So that should be fine. All right. So I'm reading through the next questions. I see. Good question. One user asks, let's go back to boundary conditions. One important aspect, very good question. One user asks, because I chose the custom boundary condition, but we could have also said, okay, why not simply use the wall, put it to wall slip, and then have a fixed value. So let's call this simply a sort of source 2. So we model the radiator or the heating, the heater at 40 degrees Celsius, right? And so this one user or one participant asks, why didn't we use a wall boundary condition, a simple wall boundary condition? So we could have put this guy to no slip. We could have put the temperature fixed value to 313, and then we're set, right? Yes, that's true. However, what this will apply in the background is a I hope I recall correctly, but I think it's going to apply a zero gradient pressure condition. No, so I would need to look it up, but it will apply a value or a type of boundary conditions to the pressure that is not ideal for this type of setup. This is why I chose the custom one, because it gave me complete flexibility on what type of condition to set for pressure. That was the main reason. It's 2 weeks ago when I set up this project, so I would need to look it up, and in the documentation we have it documented what type of pressure boundary condition is being applied if you choose the standard no slip. But yes, you're right. Essentially we're modeling a no slip but with a different type of pressure boundary condition. This is what it comes down to. So a very good question. Okay. One user asks, I hope I could answer this one. And then again, boundary conditions specifically for buoyant flows, that can be tricky, right? Depending on if you're having high temperature gradients, if you're having a lot of inlets and outlets, etc. With buoyant flow simulations, it's not straightforward to get a good boundary condition setup done. And this is where the forum is your good friend, right? Where the SimScale support is your good friend. That can walk you through it, and also where the public projects are your good friend, right? Because within these public projects, it's hundreds of buoyant flow simulations where you can go through and inspire yourself, look at what other boundary conditions are being set up, etc. Okay, moving forward. One user asks, how did you make the room translucent in the post-processing with ParaView? I assume you're referring to that guy. That's actually this setup here. So if you scroll down, there's an option that says opacity. So you can make every element of this scene, you can make it translucent. And I think it's just like very, it's visually compelling, but also helps for the engineer to understand where is happening what, if you can see actually the surrounding as translucent. So this is why I prefer this type of visualization. All right. All right. So I'm looking at the time. I will answer one last question, and then I think we need to cut it at that point. But again, the forum is there. The SimScale folks are around. There are many other engineering professionals in the forum, so I'm sure you can get your questions answered there as well. Somebody of my folks, or I will jump in, so feel free to ask your questions in the forum as well if they have not been covered here. The last question is, can I still submit my homeworks now, even for the session 1 and 2? Yes, absolutely. We do acknowledge with these workshops that it might not be the best time for everybody right now. People might be on vacation. Even right now, for a lot of people in Asia, it's not the best time to join these live sessions. So for them, the recordings are good, etc. So until 1 week after the last session, so essentially the whole July, you can submit any type of homework via of this workshop, and we'll make sure that it that somebody looks at it, because yeah, we acknowledge simple that engineers need to that it's not always the best time whenever we set up these sessions. All right. So much for today's session. I hope you did enjoy it. I hope it was a good use of your time. My last words are, as always, I cannot encourage you more to get your hands yourself on SimScale, to start exploring it yourself. It has a huge depth in terms of functionality, and a ton of people in the forum. So it's a great place to start using simulation, to start using a new tool, to start integrating simulation into your design process for ventilation and air conditioning. So I hope to see you in the forum. All right. And in 1 week, there will be session 4. My colleague Babak will hold session 4, and he will talk about contamination control with SimScale, also a very interesting topic. So I recommend you joining there as well. All right. Thanks again for your time. Take care.